Today we begin manipulating radical expressions by specifically multiplying. We had a property the other day that stated if I have a product of factors that can be split into a product of unique radical factors. Likewise, we can go the other way with that, saying if the root of a is multiplied by the root of b, that's equal to the root of a times b. Now also, if we throw constants into the mix, we have a coefficient out in front of a radical multiplied by another coefficient in front of a radical. That's equivalent to the product of the coefficients times the product of the radical factors under the radical. So let's look at this problem down here with root 5 times root 10. That fits the first property. So I have two separate radicals. I can multiply those together to get one radical that's a product of those two specific factors. Now you'll notice in root 50 I have to make sure that's simplified. Clearly it's not, because there is a perfect square factor within 50 of 25. And I know that I can break this apart now. And the square root of 25 is 5 root 2. So this is my answer here. Now, that's one way to do the problem. Some people like seeing that I can break 10 down into a product of two factors. 10 is just 5 and 2. And then if I split that apart and use this new property of multiplying any two factors I want together, root 5 times root 5 is root 25 times root 2, but I know root 25 is 5 root 2. So I get the same answer either way. I think in this case, multiplying the two together in the beginning makes more sense. This way may make sense later and actually help us out a little bit, but for now I'd multiply the two terms together. So here we go again, except this time I have coefficients out in front. I can multiply the coefficients together, so this is negative 2 times 6 and the root of 7 times 14. And here's the situation where I play around a little bit with the radical itself. I know negative 2 times 6 is negative 12. And within the radical, I'm going to need to find perfect squares if this is going to simplify. But I notice that I have this 7 multiplied by 14. And I know 14 is 7 times 2. And I can group these multiplications any way I want. This is negative 12. Root 7, or 7 times 7 for that matter, is 49, which just so happens to be a perfect square. And now I can split this apart so that it reads the square root of 49 times the square root of 2. The square root of 49 is just 7 times the square root of 2. 7 times 12 is 84, but it's going to be negative in this case, times the square root of 2, and problem solved. Now, if you don't see this 7 times 2 is equal to 14 and that gives us a perfect square, you could multiply the 7 by the 14. If you did it that way, you'd get negative 12 times the square root of 98. And then you'd have to ask yourself, well, are there any perfect squares in 98? Well, you could guess that 4 went in, but it wouldn't work. 9 doesn't go into that. 16 doesn't go into 98. 25 doesn't go into 98. 36 doesn't go into 98. 49 would be the first thing that actually went in. And notice all I'm doing is I'm checking perfect squares. So, after checking those, you find out that 49 times 2 is 98. split those apart, get root 49 times root 2, thus that's 12 times root 2 times 7, and that's negative 84 root 2. So whichever way makes sense to you, I'd go ahead and use. Now in this problem here, I'm going to get a ridiculously big number when I multiply 32 by 45. So what I like to do is see if I can simplify either of these radicals before I go ahead and multiply together. So I know that I have, in this case, 3, and there's a perfect square factor of 16 and 32. Granted, there's a perfect square factor of 4 as well, but I like guessing my largest perfect square factor. So this I know goes to 16 and 2. There's a perfect square factor of 9 and 45, so that's 2 times root 9 times 5. I'm going to break these apart. That's 3 root 16 root 2 and 2 root 9 root 5. This goes to 3 times 4 root 2, 2 times 3 root 5. This is 12 root 2 multiplied by 6 root 5. I get to multiply the coefficients together. 12 times 6 is 72, and multiply the radicals together, giving me root 10. And that's my solution. Again, you could multiply the 32 and the 45 together, but then you're getting a ridiculously large number of which you have to find perfect square factors for. Now we'll introduce variables into the problem. And I notice whatever's under the radical sign is pretty small, so I can go ahead and multiply everything together, which is my preference of problem. You'll notice in this example we now involve variables, and because what is under the radical sign is fairly small in terms of the numbers, I'm going to take and multiply these two together. Whenever I have smaller terms in terms of numbers under the radical sign, I'll multiply the two together. When these terms get larger, I'll try to break them down first. And I don't worry about variables until I've multiplied things together. So what I have is I have 12, because I can multiply the coefficients together, root 6 and 3 is 18, x to the 5th and x to the 7th is x to the 12th, and y to the 4th times y to the 18th is y to the 22nd. Now you'll notice underneath in 18 I have some perfect square factors. That's 9 times 2. X to the 12th is a perfect square because again, it's got an even power, and any even power is a perfect squared term. I know x to the 6 times x to the 6 is x to the 12th. This again is an even power, so I know y to the 11th times y to the 11th is y to the 22nd. So now I split these into any perfect square factors that are possible. And now I'll break this up. That's the square root of 9, square root of x squared, square root of y to the 22nd, and the square root of 2. I have 12 times the square root of 9, which is 3, the square root of x to the 12th, which is x to the 6th, square root of y to the 22nd, which is y to the 11th, and the square root of 2. 3 times 12 is 36, x to the 6th, y to the 11th, root 2. Now my numbers are getting a little bit bigger. I'm going to see if I can simplify at least the numerical part of these first. So let's go ahead and do that. I know I have a perfect square factor of 4 within 60. So I'll say that's 4 times 15 x to the 8th y. and there's no perfect square factors in 10. So now I'll say, well, I can break this apart, and that's going to be the square root of 4 times the square root of 15 x to the 8th y, and the square root of 10 x to the 3rd y to the 13th. Square root of 4 is 2 root 15 x to the 8th y, and root 10 x to the 3rd y to the 13th. So the next thing I'd do is I'd multiply these together. I get 2 root 150 x to the 11th y to the 14th. Now within 150, there's at least one perfect square factor that I can think of right off the bat, and that's going to be, there's a 25 that goes in there. So I have root 2 and 25 times 6 is 150. X to the 11th can be broken down into a perfect square by just subtracting 1 from that power. So I get x to the 10th x. Y to the 14th, since it's an even power, is already a perfect square, so I'll leave that as is. And then I'll take and break this apart a little bit. So I have root 25, root 10, or x to the 10th, root y to the 14th, and my non-perfect squares are the 6 and the x. Simplifying, I get 2 times 5 times x to the 5th, that's the perfect square, and y to the 7th, that's the square root of y to the 14th, root 6x. And finally, cleaning that up, I have 10 x to the 5th, y to the 7th, root 6x. And that's all simplified. So we've done the basics of multiplying radical expressions. Let me remind you again, in order for a radical expression to be simplified, you can have no perfect square factors other than 1 under the radicand. Radicands can't contain fractions, and radicals can't appear in the denominator of a fraction. We move our discussion to simplifying radical terms with fractions, and the problem with these fractions is that neither reduce, and in order to be simplified, once again, we can't have fractions underneath the radical. What I can do in each case is I can start by taking and splitting the fraction into two separate radicals. I couldn't reduce, and now I have a radical in the numerator, which is quite alright, but I have a radical in the denominator. And this brings about a new property that we're going to have to talk about, and it's something called rationalizing. Now what rationalizing is it's multiplying the radical term by a form of 1 in order to remove the radical from the denominator. So I need to find a term that I can multiply by root 7 so that it will no longer be a root. And we know that any root multiplied by itself happens to be a perfect square. So if I were to multiply root 7 by root 7, then I would get a perfect square of root 49. But I can't multiply just the denominator of this fraction by root 7 because I changed the fraction's value. I have to multiply by a form of 1. So that's why we multiply by root 7 over root 7. Thus, in the numerator we now have root 21. In the bottom of the denominator we have root 49. And the square root of 49 is a perfect square, so that leaves me with root 21 over 7. And this is simplified because I have a radical in the numerator, no radical in the denominator, so I'm clear. In this next problem, again, I can't reduce the 13 and the 20 at all, but I can split the two up. And now I see within my denominator, I do have a square root, but within that square root, there are perfect square factors. So I'm going to break that down. This goes to root 13y over root 4 times 5. And I can split that even more. That goes to root 13y over root 4 times root 5, which is root 13y over 2 root 5. And still I have a radical in my denominator. So now I have to rationalize once again by a number that will remove this root 5. Multiply any root by itself and you will get a perfect square. So I'm going to rationalize by root 5 over root 5 and end up with, in the numerator, 65y in a radical sign, and in the denominator end up with 2 root 25. And it just so happens that I have root 65y over 2 times 5, or root 65y over 5. And that satisfies the simplification process. Now these will get a little more complicated as we continue. In this problem though, however, I notice 6 and 15 reduce, because 3 goes into both, to 2 over 5, and to the 5th. Now what I'll also do in this case is notice that in n to the 5th, there is a perfect square factor within that, so I'm going to break that apart. I have root 2 over, I'm going to say that's root 5 n to the 4th times n. And I can simplify that as well. I can say that's root 2 over root n to the 4th and root 5n. Square root of n to the 4th is n squared, so that's root 2 over n squared root 5n. And still I have a radical, even though I've simplified a little bit, I have a radical in my denominator and I need to get rid of that. So I'm going to rationalize once again by the term that's in the radical in the denominator. So I multiply by a form of 1, which is going to be root 5n over root 5n. Notice my numerator term is going to go to root 10n, and having a radical in the numerator is not a problem. The denominator goes to n squared root 25 n squared. And you'll notice I can split that apart to root 10n over n squared root 25 and root n squared. Each of these terms in the radical in the denominator is a perfect square. This goes to root 10n over n squared times 5 times n, or square root of 10n over 5n cubed. And that's simplified. Let's do one more. In this case, I can reduce once again the 14 and the 20. And I'll go ahead and do that. 2 goes into both, 7 times in the numerator, and in the denominator it's going to go in 10 times. And notice also that I have some perfect squares within the variable terms. I'm going to break those down and remove those. I have 7 times x to the 4th times x. And then I have 10 y to the 6th times y. I can simplify that a little bit more into root x to the 4th root 7x over root y to the 6th root 10y, which is x squared root 7x over y cubed root 10y. I still have this term in the denominator that is in a radical, which makes it non-simplified. I must rationalize by a form of 1 to get rid of that radical sign. So I'm going to multiply by root 10y over root 10y. In the numerator, this gets me x squared root 70 xy over y cubed root 100 y squared. Now, root 100 y squared is a perfect square, so I have x squared root 70 xy over square root of 100 y squared is just 10y. So I have y cubed times 10y, which simplifies in the end to x squared root 70 xy over 10y to the 4th. We look at this final fraction, and our only question is there a perfect square factor in 70? 4 doesn't go into 70, 9 doesn't go into 70, 36 doesn't go into 70, 25 doesn't go into 70. So the answer is basically no, and this is simplified. So this process of simplification gets a little bit more difficult as we introduce fractions into the problem. Go ahead and answer these questions and fill out your lesson summary, and we'll discuss this more tomorrow.